Hi, we're a design team from Johns Hopkins, and we're excited to present to you our paper titled Minimizing Cotton Retention in Neurosurgical Procedures.
Neurosurgical operations are long and intensive medical procedures during which the surgeon must constantly have an unobscured view of the brain in order to be able to operate successfully. Currently, cotton balls are the most versatile and effective option to clear obstructions like blood and fluid from the operating area. While cotton balls allow neurosurgeons to improve visibility of the operating area, they may also be accidentally left in the brain upon completion of the surgery, as they are hard to identify from the surrounding blood and brain matter, as shown in the picture where the fresh cotton is marked with black asterisks and the blood-soaked cotton is marked with white asterisks. This can lead to a wide range of severe post-operative risks, even death. With 13.8 million neurosurgeries performed annually, this leaves 13.8 million opportunities to unintentionally leave cotton in the brain. The estimated annual cost of retained surgical items is $2.4 million for healthcare systems, with 70% of the objects being left behind absorbents. Right now, the only way of keeping track of cotton is by counting, but it is unreliable and inaccurate due to human error, and the cotton easily splits when soaked. For these severe reasons, our needs statement is such. There is a need to develop a device capable of minimizing accidental cotton ball retention after neurosurgeries. In an effort to solve this problem, we considered two general approaches, X-ray and ultrasound. First off, when testing and verifying the effectiveness of the X-ray modality, we utilized this CT scanner, a system that can be found in most hospitals around the US. Here, for testing, we used a simple setup with porcine brain hemispheres acting as human brain analogs submerged in saline solution at varying levels, from partially to fully submerged. In doing so, we could identify X-ray's capability to detect cotton in various scenarios. In these images, the cotton is placed on the top face, slightly wedged into the brain matter to ensure it stays in place. The pig brains are also partially submerged in water, as seen. The cotton ball is clearly identifiable. Here, a cotton ball was wedged deep within the brain matter, and the brain hemispheres were completely submerged in water. In this case, the cotton is drastically harder, almost impossible to identify by eye. Our X-ray results were deemed inconclusive due to the discrepancy in appearance of cotton between scans. So we believe that X-ray imaging is not effective in terms of cotton detection in brain matter.
Next, for the ultrasound modality, we conducted two experiments to test its effectiveness in detecting retained cotton balls. The first test was a size test, where we varied the size of the cotton balls, but ensured that they were placed in the same position. Here, you can see from the ultrasound images that the 15mm cotton ball on the brain on the left is clearly larger than the 10mm ball on the right. The ultrasound shadowing allows us to easily identify the darker cotton from the rest of the lighter brain matter. The same can be said for the 15mm cotton ball on the left versus the 2mm cotton ball on the right. Even when the cotton balls are very small and the same size, 3mm on the left versus 2mm on the right, the darker shadows and size differences are still identifiable in ultrasound images. The second test was a depth test, where the distance the cotton was placed in relation to the position of the ultrasound probe was varied. We accomplished this by stacking brain hemisphere halves on top of each other. As seen, both at 3cm depths and 8cm depths, the cotton balls were easily distinguished from surrounding brain matter because of the obvious ultrasound shadowing. Based on the results, we concluded that ultrasound imaging is highly effective at detecting cotton at a wide range of sizes and depths that are standard in surgeries. We conclude that there is an opportunity to create a novel ultrasound imaging device to minimize cotton retention after neurosurgical procedures. Thus, our proposed solution is a unique medical imaging device that would utilize a specialized ultrasound transducer probe and an integrated AI detection software to automatically detect the presence and general location of retained cotton. The software would quantify the contrast between cotton and the surrounding blood and brain matter by using the equation presented that divides the discrepancy between the intensity values of blood and cotton by the intensity of blood itself. Furthermore, we would use this spectral analysis data and combine it with a machine learning segmentation algorithm to create an effective cotton detection software.
This is our team. Thank you for listening.